Everyone's here. So it looks like we're still tech challenged, but somebody's supposed to be on the way. So see if we can resolve that. Uh, Thursday was the day of failures, right? We had no whiteboard and we had a hard time getting that simulation to run. And I figured out how to fix that problem. I don't understand why it's a fix, but it works. So it turns out if you follow the gouge better than we were doing in class, it will work. So let me pull it up here and I'll show you. We were trying to be all crafty and using the specific heat values that are built into the thing. As it turns out, it doesn't like those. Did everyone use that for homework 5? I haven't gone through those yet. But I've been using it for homework 5 for a while. And it seems fine. But for this problem, it totally does not. I'm not exactly sure why. I think it's because it's actually treated as a flow variable, even though it doesn't vary. And maybe with homework 5, because we only had one cell and there were symmetry planes on both sides, it somehow worked itself out. In any case, here what ends up happening is that it actually doesn't set the inlet Mach number correctly, and it starts going through crazy wild swings and blows up. Other things that I tried, which shouldn't have made a difference, but I guess it's worth talking about. Do you remember when I can't draw on the whiteboard. Do you remember when we first introduced supersonic flow and we looked at the quasi one channel? We said it can only go sonic at the narrowest part of the throat. And there was also a brief discussion saying that there can only be one throat. If you put a narrow region downstream, it'll never go sonic upstream. That'll be the new throat. So a problem you can run into in wind tunnels is that if your model suddenly uses up a huge chunk of the cross-sectional area of the wind tunnel, the model with the wind tunnel can become the throat. And so everything upstream becomes subsonic. Hi. Yeah. Yeah. We stop sharing here. So you can figure out a way to get it to work. I can't remember where it's supposed to go, but it's supposed to be different, right?
I thought it was supposed to be different, but
Or they're supposed to be one way or the other.
right.
Tried both combinations many times. It was working until last Thursday.
He's on the
I'm on the
system.
Oh, you can actually get into it.
I'm trying to see what's going on.
The desk unit seems to be working fine. It tracks everybody.
Yeah, it's not how it's going. It is not playing. on the plan to get up there and try to make it it's not playing.
Okay. I think this happened once last year, and I think I complained after the fact, and somebody came in and rebooted this thing.
Computer.
I don't know if it was a computer or whatever runs them down.
Sure, yeah.
Anyway,
Sorry.
you'll
Like
work with
You're gonna work without it?
document camera today, I guess.
Yeah.
Because we're in the middle of
Sure, yeah, okay.
All right.
If I can figure something out, I will come back.
Okay. So when we switch to whiteboard, I guess it'll be this, if I can get that. Let's see just real quick. Yes, that works. All right, so we have a workaround for the whiteboard, I guess. All right, so let's go back and finish up our discussion. Yeah, so anyway, so one consideration when you set these up is how close you set the walls to the body. If it's a high Mach number, the flow shouldn't be disturbed very far from the body. Certainly not outside of the shock or the expansion fan. There's an expansion fan. And this was running at Mach 5. So Mach 4, if you remember, we talked about the wind tunnel out at the golf course. I think the throat is about 10% of the total test section area. So there's no way we're less than 10% of the, anyway, so that's not the problem. So you can actually make the domain as small as you want. I think in the gouge, we actually carried out quite a bit further, but this should be fine. And then turns out the thing that was biting us was gamma. If you set that to the constant value, and you set that to the constant value, solution right up and runs. Let's see. See, it converges pretty quickly. I think 100 iterations is fine. Oh, this was all my different tries. Oh, I'm sorry. This is actually this is a different case. I ran this during lunch break. So this is actually Mach 8. So I went in, still up, SolidWorks, still up. Anyway, if you remember in SolidWorks, we started by drawing kind of the profile, the root airfoil viewer. And I think for this one, I set it up with an 8-degree or 20-degree shock angle. Use the calculator to find the body angle for Mach 8. As the Mach number goes up, the shock gets closer and closer, closer to the body. So there's kind of a narrow gap in there. Yeah, so this is actually Mach 8. And the reason you see a whole bunch of them here, I think this was a fine mesh, and then I think, oh yeah, sorry, this was 0 degrees, and this is 1, 2, 3, 4, and 5 degrees. For the problem, I don't know if anyone's looked at it yet. You have to do on design and off design cases. So I'd say plus minus Mach 0.5 from whatever your design case is, and then plus minus 5 degrees. If you're at the Mach 5 case, I think you can just jump straight to plus minus 5 degrees and be okay. At Mach 8, I don't know. When it starts to get a little unstable, if you do smaller increments, it's typically safer. At Mach 8, it was getting close to looking like it was going to blow up here. I think Mach numbers in the domain got up over 10. So I was thinking it wasn't going to go, but anyway, it settled out, and then all the other ones were totally benign. No issue at all. Yeah.
So you said that when you were varying the Mach number, you had to change.
Here I actually left. Oh yeah. So the geometry in the gouge sheet is for Mach 5. You could run that at Mach 8, but it's not going to look like a wave radar. the shock is going to be in some weird location. So I actually went back into SolidWorks, redesigned the WaveWriter in SolidWorks for Mach 8 and brought it in. And let's go ahead and bring it up. So this is this is the 5-degree angle of attack case. So it's no longer quite an on-design case.
You're varying angle attack between each step of generations.
Yeah. And for supersonic flow, that's definitely the safest way to go. The initial transients when you first start a simulation from scratch are pretty wild, and then it's going to blow up. That's where it's going to blow up. Going from 0 degree to 1 degree is like a pretty small change in everything. So you'll actually see the Mach number fluctuate a little bit in that case, but it settles pretty fast. So you remember in our domain, this is the break line between the inner and outer blocks of our mesh. And we designed it for the on-design case, so the shock would be right on there. And it was certainly inside of that fringe. I know it's spread out a little bit, but anyway, that was definitely on top of this. But at 5 degrees now, we've shoved the shock out away from where it's supposed to be. It's actually a little bit curved. See from the back there, this is the outlet. And now on the upper surface, good angle, we now get an expansion fan because it's now expanding. And there's actually some weirdness at the symmetry plane because I guess from the left and the right, you get 2 expansion fans and they somehow interact with each other. And so you get some dodgy stuff at the symmetry plane that's different. I'll tell you in the homework, I ask you to use the compressible calculator and also Newton's impact theory, which we'll talk about today, to estimate the pressure for the on-design case. Students always want to try it. You can try applying it for the off-design cases. The trouble is you need to know the angle that the flow is making incident to the surface, and it's not always obvious what that is. I guess you could go in here and do, say, surface streamlines and then try to do some kind of, I don't know. Anyway, the angles are hard, so if you don't feel like trying to struggle with that, don't worry. Just do the on-design case and you're good. Yeah, anyway, so there you go. Feel free to stick with the Mach 5 case if you just want to follow the gouge. But if you want to use the techniques in the gouge and do your own thing, I know it works at least up to Mach 8. You could try going higher. I don't know when it'll become a problem. When everything is sharp and you're using free slip boundary conditions, then doesn't seem like it's too awful. Anyway, that's probably enough for that. So let's see if we can figure out how to use this document now. Switch to it. And find an angle that works. Right. See if this works. So last time we had a lecture, which I guess was like a week ago, we were talking about slender bodies. And we used this kind of bizarre theory where you assumed if you had some kind of body of revolution, that as it passed through some kind of a plane, it was cutting a cross section out of here, and the fluid would somehow have to get displaced and come around and squish from the bottom to the top. And show up. And that process of the fluid moving around there was creating a lift force on the body. And so we went through some simple analysis, and the end result was this Pretty simple equations. The lift was pi rho d squared alpha times radius of the tail squared minus radius of the nose squared. And if it's something like I drew up at the top, or it's pointy at the front and blunt at the back, then so for blunt tail, then you just get lift equals pi rho e squared alpha r. I think they called it RB for R base squared. And if you turn that into a CL, then you just get 2 pi, I think. Or, I'm sorry, 2 alpha. Stupid simple equation. So there's one other thing that we can do with this. If you look at this crazy simple equation, if it's pointing at both sides, these are both 0, and so the whole thing vanishes. There's no lift. If they're both the same size, like a cylinder going through the flow, then again, the lift is 0. But you can actually kind of throw together 3 variations of this. You can have something that's pointing at the front, then a cylindrical section, and then something that's pointing at the back. And it turns out you can sort of apply this equation 3 times. This front bit is the case where CL is 2 alpha. The back bit is the reverse, so our nose is there and our tail goes away. So it's the same thing with a minus sign. So here I've got 2 alpha here, and I've got 2 alpha here. And the middle bit is 0 because they cancel each other out. And so I guess the one takeaway of this stupid simple theory is that anything, some body of revolution set up like that is statically unstable. If you perturb it, you give it an alpha, then the resulting forces on it create a moment, which is destabilizing and make it go further. So you never make a missile this way without fins, it's going to tumble. No way around it. So you look at things like SpaceX rockets, what do? They have a very active control system that tries to keep it from diverging so far that they can't fix it. And some of their spectacular wrecks at the beginning are times when the actuators failed. Spun out of control and blew it up. All right. Good. So let's see. Let's get on to some slightly newer stuff. We can use that same approach. It's kind of an added mass approach for say a slender airfoil. Say it's a wing. It's got some cross-section area. It's not a body of revolution, so it's got from the back. Look at it. Say something like that. It's got some thickness to it, and it's going at supersonic flows. So we can apply the same approach. Again, it's assuming added mass. So if the thing is at some angle of attack, alpha greater than 1, and it's going to essentially take fluid from the lower surface and squish it around the upper surface, exactly like the body of revolution did. The only thing we had to figure out for the body of revolution, the magic bit, was what is the volume of air that is being moved. And it turned out that was the displaced air from the body itself. For this, it's not. Turns out what works better is assuming the volume of air, basically a slice through here, that has whatever the local span is. So here's my local span, is B of X, some big B back. And so the diameter here would be B of X. And so we apply essentially the same equation. We have the lift prime, which is the sectional lift or sectional lift, was big U pdx m of x minus WA of x
Just like
Sorry. And if you remember, this was the mass per length of displaced fluid. And this was the speed due to alpha. So, yeah. So if it's a steady problem, then W steady WA of X just becomes U times alpha. And our MX it's just going to be rho, sorry, not U, eraser, rho times the area of that cross section. So pi b over 2 20 squared. And so we can go ahead and plug that in. Lift. Is it focusing? Yeah, like an autofocus switch here. It's okay. So lift is rho u squared I alpha big B squared over 4. This is integrated on nose to tail. And we can make a substitution. You guys probably know this from homework 4. We had aspect ratio is P squared over S. So subbing that in, we get lift is rho U squared I alpha S aspect ratio over 4. And if we turn that into a coefficient, we'll get CL divided by half rho U squared. We end up with pi alpha times aspect ratio over 2. That, let's see if I can find it here. I think Platzer's got a picture of this. His notes open. I do not. Yep. That's it. Guess that's what I was looking at last. Yeah, so here's CL as a function of alpha. Here's the aspect ratio. So here's experimental data. And here's that line equation we just derived. So you can see if aspect ratio is less than 1. Okay, so slender body. Aspect ratio 1 for supersonic thing is actually still moderately big. So you get down into this range and the theory actually all from ridiculously simple mechanics, just that added mass. Let's see what else. Yeah, so I guess we can expand it slightly further. We now have a slender body theory and we have a slender wing theory. And so as it turns out, we can actually just add them together to get kind of a more general equation. So lift equals rho U squared. And then we have big B squared over 4 minus R squared plus 4R to the 4th over B squared. Where R is the base radius for the body of revolution, and B is the span, that trailing edge of our wing. I haven't tried to run a CFD solution to see how close that is. I guess at some point we could try to do a problem like that. The challenge is always to come up with problems that don't take ginormous numbers of mesh points. Not so much for you guys, but more for the DL guys struggle with compute power a lot of times. All right. So that's probably all we'll talk about in that section. So let's go on to, I think it's Platzer's chapter 7. It's no, sorry, skip one, chapter 6. I think he calls hypersonics. And we're not going to do a lot with hypersonics. He doesn't go into a whole lot. But we're going to introduce this thing called impact theory. Everyone's used that before. But it's actually, it's a great follow-on to Newton's approach for estimating performance of a wing. Essentially, if you've got some wing with incident flow, some d infinity, some alpha, he thought that the only thing we needed to worry about was the particles that basically come up and hit this thing and got deflected. So do a momentum calculation and figure out what the lift should be. But what he neglected, of course, is that in low speed flow, supersonic flow, the upper surface actually contributes heavily to the lift of the vehicle. Well, it turns out as the Mach number gets higher and higher and higher, we have this shock wave out here, this wedge. But the higher the Mach number, the closer this gap is. So the turning point of the particles gets nearer and nearer to the surface. So sort of an asymptotic theory is it's Mach number high enough that particles get turned right at the surface and all of their momentum gets transferred to the body. And when we did this for supersonic flow, so some kind of a airfoil here, we would take a point up here and we would look at the local angle, theta A, and then a point back here, and again, we'd look at the local angle with respect to free streams, theta P. And so here you get compression, and here you get expansion, and we have that CP equals 2 theta over theta. I think it's all right. Yeah, so anyway, so you had to treat both sides. You didn't have to treat this. You didn't have to know what was happening upstream. You just had to know what its local angle was. It all worked out fine. For hypersonics, if you remember, I barely talked about it, but when on like the diamond airfoil, we've got that rooftop. So start with shock up here, and then we have this expansion fan. And if you remember, there's a starting angle, omega 1, and then there's an omega 2. As the flow expands and the streamlines come up in the curve, stay tangent to the surface. Well, this was all came from this thing called the Prandtl-Meyer function, and the Prandtl-Meyer function has a limit. If I can find a plot, but it's something like this. This is Mach, this is omega. And it does something like this. It goes out to infinity, and there's some fixed angle. Off the top of my head, I don't remember what it is, like 120 degrees or something like that. So you can only expand the flow so far. So when you start talking about hypersonics, if the Mach number in this region is already super high, you can imagine that we may not be able to expand it all the way to be tangent with this downstream surface. If you have a body where it's more like a wedge, and it has to turn really hard, for sure, you're going to run into a limit. The flow can't do that. It's going to go to Mach infinity, which means absolute zero pressure. Won't do it. And so at some angle, it's just going to, and you'll end up getting like a big old stalled mess back here. It's just really hard to calculate. But in the end, the pressure is close to P infinity. And that kind of boat tail region. And so that's really what Newton's impact theory does. On the lower, on the lower surface here, where we would have a shock, we're compressing the flow. We'll compute a pressure coefficient there. So we're actually applying a force. But on the top, even if the top is an expansion, we're going to assume that it's just free stream. So pressure coefficient is 0. Doesn't contribute to the overall lift. All right, so let's just sketch it out here. So here's my wing. Got some angle of attack. Got some velocity coming in. And it's resulting in some normal force. Up on top. My wing has some area. A. And so there's a sketch out regions here. This here is going to be what a cosine alpha, and this is going to be a sine alpha. And the velocity that's hitting normal is going to be a component of this. It will be u times sine alpha. And so just solving for Newton's second law, we have the normal force m dot times velocity, which is going to be rho u a sine alpha. That's the m dot. Times the velocity is u sine alpha. And so solving for n over area for pressure, we'll get u squared sine squared alpha. And CP will be n over a over f rho u squared. And if we plug that stuff in, the rho u squared is going to cancel out here, and I get 2 sine squared alpha. Okay, so that's it. That's my CP. Only on compression surfaces. For expansion, CP is assumed to be 0. I can actually go ahead and apply this to a problem. So I guess it's the same problem. We can solve for CL, CD, and CN. So CN will be the coefficient in the normal direction. So that's half integral 0 to C of CP lower minus CP upper times dx. But these are just constants in this case. So this will just be our 2 sine squared alpha. And then if we want to find the lift coefficient, CL. Oops. It's going to be Cn times cosine alpha, which is 2 sine squared alpha cos alpha. And then CD will just be Cn sine alpha, which is 2 sine cubed alpha. I suppose, I don't know, maybe we could do a CFX problem at some point. I've tried it. If you plot that out, get something like this, like CL peaks at something like 0.8. And here's alpha from 0 to 90 degrees. And CL looks something like right that. And then CD, if we have a second axis over here for CD, going up to a value of 2. Alpha is 90 degrees, that'll be 1. So asymptotically approach a value of 2. All right. So super simple theory. Let's go and apply it to something, you know, I call it practical. This was from a PhD student in Mikado. We did a guest lecture when Hobson taught this class 4 years ago, I guess. So let's take some super simple blunt shape here. And then here's Mach equal to 10. And we have P infinity equals 7 kPascals. And this is 45 degrees. This is 45 degrees. I think he labels the points A, B, C, D. So I didn't draw quite to scale. It's basically just.
Come on, man. Why don't you come over here? Yeah, there we go. Kiss on touch.
All right. Little childcare going on in the background. Okay, so let's apply these equations then. So we have P minus P infinity, rho P infinity squared, sine squared theta. And let's see, it divides by P infinity, so P minus P infinity over P infinity is rho infinity over P infinity, P infinity squared sine squared theta. And our A infinity squared is gamma infinity over rho infinity. You remember back from our derivation of speed of sound. So we can flip that around. So rho infinity over P infinity gamma over A infinity squared. So let's take that and let's plug it in here. So I'll get gamma A infinity squared, it's B infinity squared sine squared alpha. I guess I swapped the theta. And the B infinity or A infinity is Mach gamma and infinity squared sine squared theta. And then this P minus P infinity over P infinity is P over P infinity minus 1. So we can take the 1 to the other side. So P over P infinity equals 1 minus gamma Mach squared sine squared theta. And last we can solve for P. So P equals infinity 1 minus gamma 3 squared sine squared theta. All right, so we can go ahead and apply this to our 3 faces. So on pressure AB, it's going to also equal pressure CD, since they're both at the same angle. So they'll be 7 kilopascals, 1 minus 1.4 gamma Mach squared, so typically squared sine squared 45 degrees. Sine of 45 degrees is what, root 2 over 2. So square it, that's a half. So anyway, crunch through the numbers and I think you get 497 kilopascals. So the forces get pretty brutal. We had 7 kilopascals of air in the free stream. We're now not quite 100 times that much. So pressures get big in a hurry. Mach 10 is still slow for reentry vehicles. Although 7 kilopascals is high for atmosphere. All right, so there's those two surfaces, and then we still have the front surface. So pressure EC going to be 7 kilopascals times 1 minus 1.4 for gamma, and the Mach squared, sine squared 90 degrees, 1. So you end up with 987 pascals. Anyway, super easy to apply. Give it a go. You guys get to do this, you said, for homework 6. 8 is, I think, hopefully clear on the on-design case because you drew SolidWorks that way. But when you start applying the angle of attack, the angles don't work the way you think they would work. In the general case, you have some arbitrary body, and there's, you want to apply this theory, you find some little dA on that surface, and you'd have to find an outward facing normal. And then you've got your free stream coming in. And then what you'd want to do is you'd want to make a plane between these two and measure this angle here, let's call it phi, between the free stream speed and the normal. And then the theta that you want to use would be what, pi over 2 minus phi. The trick is in doing all that geometry. When you take the airfoil and move it, then I mean, you could do it in SolidWorks actually. If you're good with planes and vectors inside of SolidWorks, you can have it do that for you. Anyway, the theory doesn't work well enough to merit that level of effort, I think. So I would apply it to the on-design case and you'll get an idea of how close it is. At Mach 5, it's not super awesome, but the higher the Mach number, the better it gets. So if anyone wants to try a high Mach number wavewriter, they can compare.
It's like a little bit small.
Yeah, it's the shot gets closer and closer to the body, and anything we neglect from expansion areas become the fact that we neglect it becomes more and more accurate. All right. Anyway, that's Newton impact theory. There's actually a modified version of this. So in our CP is 2 sine squared alpha. So if we imagine hitting a blunt body, so you've got missile with a blunt leading edge, or I guess reentry capsule, you've got a stagnation point coming up there. So at that point, alpha is 90 degrees, and so CP is 2. That's your peak. But it turns out if you actually go into the Virginia Tech calculator and you try to compute the stagnation CP for high Mach numbers, it turns out not quite B2. And so there's some modifications you can make to try to get that stagnation value a little bit better. They call it the modified Newtonian impact theory. So let's see here. If we had that equation that CP was 2 sine squared theta, and this 2, that was our stagnation CP. So let's replace that. Let's call it CP naught for stagnation, sine squared theta. And now let's try to figure out a better way to come up with what that CP naught is. So let's say that CP over CP naught is our sine squared theta. which is P minus P infinity over P naught minus P infinity. And from we actually don't drive these equations in here, but they're in the books if anyone wants to dig. When we do all of the normal shock relations, we always skip over it and go straight to the Virginia Tech calculator, but there's a equation for P naught over P infinity, and it's a gamma plus 1. It's an ugly equation, infinity squared over 2 raised to the gamma over gamma minus 1 over 2 gamma and infinity squared over gamma plus 1 minus gamma minus 1 over gamma plus 1 raised to the 1 over gamma minus 1. Yeah, you can find it, and that's what's built into the Virginia Tech compressible calculator. If you find that. So let's take this and let's plug it into, let's divide top and bottom by P infinity here. So we'll get CP equals P minus P infinity over half rho P infinity squared, which equals P over P infinity minus 1 over, and let's do this swap for, we have to half rho infinity P infinity squared. That's half gamma P infinity log infinity squared. So let's take that and sub it in here. What we're left with is gamma and infinity squared over 2. And now let's apply this at the stagnation point. So we have Cp naught n is going to be gamma plus 1 infinity squared over 2 to the gamma over gamma minus 1 over 2 gamma infinity squared. Gamma plus 1 minus gamma minus 1 over gamma plus 1. 1 over gamma minus 1 times this stuff. Gamma infinity squared over 2. All right. So again, an ugly equation. There's a plot for it. You do it as a function of Mach. So there's frame. Here's my Cp naught n. Here's my Mach. Looks something like this. And asymptotically, as Mach goes to infinity. If you do a limit equation on this for Mach going to infinity, it actually has a limit. So limit as Mach goes to infinity, this becomes gamma plus 1 over 2 to the gamma minus 1 over 2 gamma plus 1 raised to the 1 over gamma minus 1 gamma over 2. All right, and that has a value for air. It's 1.834. Only a function of gamma, right? So it's Cp naught n. It's from his notes. I'm trying to think of where the n would come from. He introduces it. It's technically the CPU should be getting at stagnation. So anyway, so it's only a function of gamma, so you work with some other material and get different curves, but they all look kind of the same and they're all asymptotic. So anyway, so this is modified theory. All you would do now is take this 1.839 and you would substitute it back up into here for if you want to apply modified theory. And I believe I ask you to do both. Math is trivial. So it takes you 5 minutes less. You'll find the higher, again, the higher the Mach number, the better it works. It still falls into the category, I guess I'd call first order. So if it's not a complicated body, it works pretty well. The more complicated things get, we'll trust it. It's kind of like perturbation theory for elastic assignments. And I think that probably is as much as we want to do there. So I might just call it for the day. I'll tell you, we're getting pretty close to the end of the course material. There's just a little bit, one more section we want to do. Looking at swept wings. And then there's a homework assignment that goes with that. That's another CFX problem that's pretty fun. And that'll be it. We'll meet Thursday. Might be able to go through all that material then. I'll try to get the last homework assignment posted. You guys are pretty much good. All the homeworks will be due end of finals week. So I'll give you some extra room around there to get stuff finished. It's kind of hopefully a hard deadline. Next week, I don't know. We'll figure it out Thursday. And I'm out of town next week, Thursday. I'm happy to come in Tuesday even if we don't have material. I'm happy to meet if people have questions on stuff. We'll see. I'd probably go through some of the setup for that homework problem. Talk about some of the things to do in there. Yeah, and that's probably it. I don't know if we'll need to meet at all the following be around. Who knows? Maybe we'll have a whiteboard Thursday.
Like even if we have the same social study and you start out.
I actually made up. I think CP and C ball were still.
Oh, they were so
sure, but I'm not using them.
Oh, I
I
see.
just replaced gamma instead of being ratio to. I just hardwired the number.
Okay.
And then same with our gas.
And that.
And they're in the gouge for the expressions. So we use those values. That's what actually.
Yeah, but they would change depending on.
They would if this goes to 10%.
Okay.
Doesn't.
Okay.
Or at least I don't know if I make it. The irritating thing is that even when the case was like blowing up these numbers and if you stop the solution and look at it, and you look at the CP values of the solution, they are dead on. Constant numbers, they're not varying. But for some reason, if you try using them,
And so you wanted us to do the alpha suite of negative band positives one month.
yeah, and then at 0, you know, two Mach numbers on one of them. Kappa,
Oh, I see.
Kappa Mach above, Kappa Mach.
So,
All those cases will kind of mess with the non-design nature of the problem.
Sounds good.
it's got, well, so actually,
You know, so I have an AMD processor on a workstation. Do I use Intel?
Yeah.
Local parallel?
I-
Or do I?
See, like,
Can I
heard it.
Probably,
Okay,
pretty sure so.
okay,
I don't have the AMDs,
okay.
but I think
See,
the two families, but I think, the difference between like a PC versus a Mac.
Mhm.
right.
So,
So that whole.
Right.
And then the Microsoft inside, is that something else?
And then take.
This
that
is for
view
my
here.
workstation over at the Turbo Propulsion Lab.
Okay.
Ben is saying that, and I think you're Microsoft.
Oh.
He said, but he said he wasn't sure.
Put that in.
well, so CFX kind of compiles in the
Okay.
parallel processing language they need.
Okay,
So it should all be in there. If you're on an AMD chip, I would just try it.
sounds good.
Yeah, that's perfect, yeah.
Lines and make sure you know that I don't think it should be a problem.
Mhm.
Geez, surprised. I've never had anybody complain about it. Or can't believe none of my students have had
And if you look
AMDs
in
before.
Makes sense.
A lot of the,
You're looking at the.
test pilots have big old gaming machines. A lot of those are AMD. Way more compute power for the buck.
Mhm. All right, sounds good. I'll let him know then.
Yeah, okay.
But I wasn't really sure.